In this video, we're going to talk about the evidence for dark matter in astronomy, and specifically the evidence for dark matter within galaxies. To do this, we need to discuss what a rotation curve is, because this becomes one of the main tools that astronomers use to discern the indirect effects of dark matter. So what a rotation curve is a graph that plots the speed of an object that's orbiting versus how far away it is from the center of whatever the orbiting system is. So orbital speed versus orbital radius. And the simplest example would be a solid disk of material, something like a vinyl record, where every piece of material takes the same amount of time to orbit around the center as the record spins, which means for a piece of the record that's furthest out, in order to spin in the same amount of time as something near the center, it needs to go faster. And so if I wanted to plot a very simple rotation curve, a solid disk rotation curve, I would have speed on the y-axis, distance on the x-axis, and I would have a line that increases with distance. Now, we might be able to talk about whether it's an exponential line or a straight line. In this case, I'm just going to draw a straight line to show that with increasing distance, I have increasing speed. In astronomy, when we're talking about orbits, we're usually describing something like planets orbiting around a star or stars orbiting around the center of a galaxy. And so we need to think of how gravity holds things in orbit. One of the rules that we know about in astronomy is that the speed of something in an orbit depends on how much mass is interior to the orbit. And so the bigger the mass interior to the orbit, the bigger the gravitational force you'll have on the orbiting object. Bigger gravitational force means bigger acceleration, bigger orbital speed that results from this. So more interior mass means higher orbital speed. Now, if the mass is mainly concentrated at the center of the system, then the speed will decrease with distance. And so what that means is you'll have most of the mass concentrated in the center, for example, the sun at the center of our solar system. And as you get further away, the things that are orbiting have basically a constant amount of mass inside their orbit. So the further away you get, the further away you're getting from the massive object, and you'll have a decrease in orbital speed because of a decrease in gravitational force. So a good example of a system like this would be our solar system, and here is the rotation curve for our solar system. As you get further out from the sun, this orbital speed goes down. But what about the galaxy? When we look at a galaxy like our own or like other spiral galaxies, what we see is that you've got more luminosity near the center of the galaxy. And so if you're just going by the luminous material, you would expect that there's more mass concentrated at the center of the galaxy. And so its rotation curve should be somewhat similar to what the solar systems would be like. So you'd start with high speed near the center of the galaxy, and as you get further away from the center, the orbital speed of stars and other material would go down. But that's actually not what is measured. What is actually measured is very different from this. And I've drawn a rough rotation curve for what astronomers actually measure for our Milky Way galaxy. By measuring the speeds of stars and clouds of hydrogen within the galaxy using Doppler shift measurements, what we find is that the speeds of these objects, as you get farther away from the center of the galaxy, stay roughly constant. This is kind of strange. A galaxy in which the stars have roughly constant speed as you get further away from the center is going to be very different in some respects than a galaxy that doesn't have constant speeds. I'm going to illustrate this with an animation that shows a galaxy on the left which has its mass all concentrated at the center, and then a galaxy on the right which has its mass fairly evenly distributed as you get further away from the center. And this allows for a constant orbital speed the further away you get from the center of the galaxy. So what we see on the left is a galaxy that has orbital speeds slower as you get further from the center, and on the right is a galaxy with high speeds that stay constant further from the center. So how is a rotation curve like that possible? In order to keep the speeds constant at an increasing distance, there needs to be mass distributed throughout the entire orbital system, not just at the center. But you might ask, the galaxy is brightest at the center, so what is this other mass? Well, that's a problem unless we consider that perhaps all the mass of the galaxy doesn't give off light. And so that leads us to the idea of dark matter, that there's additional mass within our galaxy that isn't luminous. But what is the dark matter? All we mean by that is that dark matter is material that is not luminous, that is, it's not giving off light. It has gravitational effects, but doesn't interact with extra. Dark matter is material that doesn't give off light, it's not luminous. It does have gravitational effects on the things around it, but it doesn't interact with other things using the electromagnetic force. The term dark matter is just a placeholding term that we're using to describe this material until we figure out what it is, what the particles are, or what the material is. We don't really know yet what makes up all of the dark matter. There's a lot of different ideas that astronomers and particle physicists have for what dark matter is, but we haven't quite pinned it down yet. This image that I'm showing you is a depiction of what the Milky Way might look like from the outside, including the luminous matter, but then the blue color that you see shows the distribution of where the dark matter would be in the galaxy and throughout the halo of the Milky Way galaxy. It's evenly distributed throughout. So as you get further away from the center, you have an increase in mass interior to the orbits of those stars. This means more gravitational force as you get further away, and that means the stars that are further out are able to maintain high orbital velocities. And we don't notice this just for the Milky Way galaxy. We see this in other galaxies as well. So for example, on the left is an image of NGC 3198, and on the right is its measured rotation curve. Again, this is very similar to the Milky Way's rotation curve, where you have a roughly constant orbital speed the further away you get from the center. Other galaxies as well show this same pattern of rotation curves. This is an image that comes from a peer-reviewed journal publication from Vera Rubin and her collaborators that was published in the late 1970s. Vera Rubin did a lot of the work in the 1960s and 1970s measuring the rotation curves of other galaxies. There's other evidence that we have for dark matter that points to dark matter being an actual material or particle and not just a modification to the equations that we have for gravity. For example, the image that I'm showing you here is of the bullet cluster, which astronomers believe is the collision of two galaxy clusters. And the gas that was inside of the galaxy clusters collided and was compressed and slowed down. And that gas is hot, it's giving off X-rays, and that X-ray emission is shown with the pink and the red color here. But the mass distribution of these galaxy clusters, that is the center of mass, just kept going. And the blue shows the mass distribution of the galaxy clusters themselves. Notice how it's offset from where the hot gas is located. Now, how do we know what the center of the mass distributions of these galaxy clusters is? Astronomers measured that using something called gravitational lensing, which is using the bending of light around these clusters. That points to something other than a fault in our equations of gravity. It could be that this is very good evidence for dark matter being an actual particle.